So before we begin, a couple of quick announcements. So first of all, I think some of you might have attended the tutorials on probability, linear algebra, and Python. So as I mentioned before, these were all prerequisites, but we are giving you a quick tutorial so that you can refresh your memory. So I did not see a lot of people attending these tutorials. It might be because you already are familiar with probability and so linear algebra and Python and so on. However, the videos of the tutorials are available in your Moodle page. So if you go to the Moodle, you should be able to see all the free tutorial recordings as well as the collab notebooks for these tutorials. So if you want to refresh your memory, you can do that. And another important announcement. So I see only half of the class has submitted their assignment 0. So this was yesterday night. So maybe a lot of you submitted today. I did not check. But please make sure you submit A0. I know it is not graded, so it doesn't count for anything, but it helps you to learn how to use Gradescope. Okay, so because in the past, we have had several students who will come to assignment 1 and not tag any questions at all. If you don't tag a question, you get a 0 for that question, irrespective of whether you have answered it or not. If you don't tag, then the TAs cannot see the answer. So you have to tag your question so that the TAs can see and evaluate your answer. We will not accept any request which says, okay, I forgot to tag, because assignment 0 is your exercise for learning how to tag. So it's very simple. Even if you don't have answers for the questions, just submit a random PDF, but learn how to tag your questions. Okay, so if you have not done it, please do it by tonight. I think the deadline is 10 p.m. Okay, and the first assignment will be released tonight, which is graded, right? So and one quick warning or announcement, so before you see the first assignment. So when you see the first assignment, you might actually see some content which we haven't covered yet. It's mostly because of the 30 minutes we lost in the previous week. But you should be able to answer more than half of this assignment already starting today. Okay, so start with your assignment. So whatever questions we haven't covered, we are going to cover in the next week. So I think assignment has 3 weeks. So you can start with the assignment this week, and there may be 1 or 2 questions which we might only cover next week. It's because we are lagging a little bit. Okay, so but that's normal. So even for the future assignments, we are going to see situations where when we release the assignment, you can do half of it, but the next week you should be able to do all of the assignment. Okay. Well, also we had 1 week gap. I don't know how many of you refreshed your memory from the first lecture, or you might be a bit lost. I'll try to do a very quick recap anyways. But before that, are there any questions about tutorials or assignments? Yeah.
For the assignments, since we're using Gradescope, and I think you said that most of the assignments are going to be in Python, but is there, do we submit the Python code on Gradescope also?
Oh, those instructions will be released with the assignment. So I guess you will be submitting your report in Gradescope and the notebooks in Moodle. But the instructions will be explained clearly in the assignment itself. Okay, so maybe let's get started. So, okay, so to give you a very quick recap, I'm not going to write anything. So last week we started with the basic problem in machine learning, which is the problem of prediction, right? So in prediction, given some input, we are interested in predicting some output, right? If this output is a real variable, then it happens to be regression problem, right? So if it is a categorical variable, where you have a bunch of options like classes, then it is classification problem, right? I think we did 1 standard example for regression, so we did linear regression, where we had this housing price prediction problem, where the idea is, given the size of the house, we are interested in predicting the price, right? So, and this was the solution that we had, right? So here the blue dots are your training examples, and you fit a linear model for this training example. So the linear model was basically W transpose X, right? So your Y hat was W transpose, yes. And if I want to expand this, it's basically W0 plus W1x, where W0 is the bias, right? And we also solved the least square objective for finding these W0 and W1, right? Like so, so this is the least squares objective, remember, and we got this line. Now to evaluate this line, we also talked about root mean square error, which is basically square root of the least square, which is also divided by n. So just to make sure that this error doesn't depend on the value of n and also not in the same scale, right? So, and we found that this simple model is off approximately by 50K, okay? So, but still, it looks like a decent model to predict the size of the house, right? So this is where we stopped. So as a summary of linear regression, okay. So the model that we have seen is basically y hat is equal to W transpose X, right? So this is an example for a linear model. So can someone tell me how would you figure out if a model is linear? Yep.
It represents the equation of a line.
Okay, it represents the line. Okay, any other answer?
By developing terms,
Sorry?
and to just develop and see that it's a function.
How would you see that it's linear? That's what I'm asking.
If you develop the omega transpose,
Okay, so anyone else? Yeah.
The parameters just get scaled and added together.
Sorry, can you please repeat?
The parameters, they just get scaled and added together.
Okay, so the parameters just get scaled and added in some sort of linear combination. Okay, so and there are also some answers in the Zoom call, like so when it is linear with respect to the parameters. So I think whatever all of you were trying to say is like similar to the definition that we had from the previous week, which is basically the model should be linear with respect to the parameters, right? Like in this case, it's simple W transpose X, which means, or if I have to expand this, it's W0 plus W1X, right? Now, in this case, like it is just a linear combination of the parameters. And this equation is linear with respect to the parameters, right? Like so, on the other hand, like we also discussed that, for example, if I have a model like this, is this linear or non-linear? Okay, how many of you think this is a non-linear model? Okay, how many of you think this is a linear model? Okay, I would assume that the majority is linear, so it's still linear, right? Like because it is still linear combination of the weights or the parameters, right? Like so you have x square, which is input, which is non-linear, but the model is still linear. Okay, so this is also an example for a linear model. We are going to see such models today. Okay, now, so what are the parameters of this model? So what are the parameters of this linear model? Yeah, W0 and W1, right? Yeah, just the W vector. Okay, you can be more confident. So, okay, and the objective function we used is basically the least square objective. If I have to put it in the matrix notation, it is 1 over 2 y minus xw transpose y minus xw, right? This is basically y minus wx the whole square. I'm writing it in matrix notation. And the solution for this, which we derived last lecture, is x transpose x inverse x transpose y, right? Okay, and we also had a metric, right? Like for every problem, we need a metric on which we are evaluating our system. So what was the metric? So the metric was root mean square error, which is basically square root of 2 times E of W over N. Okay, so this is where we stopped. right? Okay. So today we are going to see more problems and solutions. Okay, so but to introduce some of the basic concepts in machine learning, I'm going to take a synthetic example to begin with. Okay, so the synthetic example I'm going to consider is basically a sine function. Okay, I'm going to sample some data points from a sine function, and I'm going to see if I can fit a model which is going to make accurate predictions. Okay, so my real target y is going to be sine of 2 pi of x plus some epsilon. Okay, so where this epsilon is a small. Okay, sometimes your voice gets doubled. Okay, it might be because I'll try to keep it a bit low. Okay, so yeah, so epsilon is basically some small Gaussian noise. Okay, so it's sampled from a Gaussian distribution. Let us say with 0 mean and some 0.3 standard deviation. So this is the mean of the Gaussian, and this is the standard deviation of the Gaussian. Okay, now this is how my data is going to be looking like. So here you can see that this is the actual sine function, and I add some epsilon noise. So for example, if I have to sample here, I'll sample this point plus some epsilon. So in this case, the noise turns out to be a little bit positive. So the data point lies here. Okay, and in this case, the data point is here. Okay, so I sampled 10 such points. Okay, now given these 10 points, can you fit a model which will make accurate prediction? For example, let's say I give you this is the x. Now what is the corresponding y, right? So the corresponding y is this, right? Now, I want to highlight two things before we continue. So in real life problem, we will never have access to this true function. Okay, in this case, I tell you that the true function is sine 2 pi of x, right? Like so, in real world, we are not going to have access to the true function. So even in the housing price prediction example, like nobody told us what is the real function that is going to fit the housing price effectively, right? Like so, but here we know what is the true function because I created it. And every time I move things a little bit faster, the video lags. Okay. Now, so the second point I want to highlight here is about the noise. Okay, so in this case, instead of using exactly points from the sine function, I added a bit of noise, which is also kind of similar to how real life data would look like because in reality, whenever you measure some features, there might be errors because of the instrument, like instrumental errors, or there may be true stochastic noise that is there in the system, right? Like so the real life data is also noisy. So to simulate these things, like we have this synthetic data set with which we are going to work like. Okay. Now, how do we come up with a model to solve this problem, right? So imagine you don't see that blue line, you don't see the sine curve. Okay, you just see the data points. Maybe I should have had another figure which just has the data points. Okay, so you just see the data points. So how would you come up with a regression model to solve this? Okay, so the first obvious choice is to take the linear regression model that we have learned so far and directly apply it here. Okay, now throughout this course, like every time we see a new problem, we will first try to fit the model that we already know, and if it works fine, it works fine, right? Like so we're happy. If it doesn't work fine, then we are going to come up with new models which are better than previous models. Okay, so first let's see how the linear regression model is going to work for this particular data points. Now, can someone predict how the linear regression solution would look like? Yeah. Yeah. So it's going to be a slope, right? Like which side? From, I think it's going to be something like this, right? Okay, so let's see how it looks like. Just 1 second, water. So this is the linear regression solution. Okay, so in this case, I have my x. I make my prediction as W0 as W1x, and I find W by using the solution that I already have, and this is the line that I'm getting. Okay, is this a good fit? No. Now, how do we improve this? Yep.
I think we had some degree of freedom.
Okay, so we can add some degree of freedom, right? Like, so this looks like a very restricted model, right? Like, so it can only fit a line. But what we want is like more than a line. We want a non-linear function, right? So now how do we do that? Okay, so one simple solution as he suggests, okay, so this is a class of 100+ students. I will never get the names, but still I will try to learn some names. So what's your name? Sorry?
Julian.
Julian. Okay, so as Julian suggested, we can just fit something which has more degrees of freedom. So what we are going to do is, instead of considering just W0 plus W1x, we are going to add more degrees. Okay, so I'm going to construct a polynomial, okay, which has m degrees. So W2 plus W2x squared plus Wm x power m. Okay, now y hat of x hat x. So this just means that y hat is a function of x, and it has some parameters w. Okay, now in this case, okay, before we continue, like a quick note about my notations. Okay, so whenever I say x square, okay, it just means x raised to the power of 2. But whenever I say x, this kind of 2, so this is the x of the second example. Okay, and whenever I say x2 like this, it is the second feature of x. So I will try to stick to the notations, but you can see me deviating from the notations once in a while. But again, if you go read the textbooks, different textbooks have different notations. And even when you read research papers, they are going to have different notations. There is no standard in notation, so you have to learn to be a little bit robust to notation. So if I switch notations, don't get confused, like ask me, I'm going to just clarify. Okay, but I will try to stick to these notations. Okay, now I'll take this equation. Okay, let's put it here. Now we can use the same trick to bring the bias inside. So I can just say W0 times 1 plus W1x plus W2x squared plus Wm x power m, right? So I can also call this as x power 0 because anything power 0 is 1, right? So now I can write the whole thing as summation j is equal to 0 to m wj x power j. Okay, if we let w is equal to w0 w1 to wm, the w vector. Okay, similarly x is going to be a vector of x power 0, x power 1, x power m. Okay, now my model is going to look like w transpose x again. Okay, now this w transpose x, right, or this equation is actually a non-linear function of x. Okay, but it is still a linear function of the parameters, which means this is still a linear model, and I don't need to reinvent a solution here. Like I can exactly use the same solution as before. Okay, so I can just use the same error function, which is 1 over 2 summation over n is equal to 1 to capital N y hat of x power n, sorry, x nth example minus y of n the whole square. Right? Now this is still a quadratic function of w, which means based on yesterday's like based on last lecture, we know that when you have a quadratic loss function, you have a unique solution, and the unique solution is basically the x transpose x inverse x transpose y, right? It is just that x is a vector instead of a scalar, so nothing else changes. Okay, now this means that you can take linear regression and fit non-linear functions. Okay, now let's see what happens if I change the degree of this polynomial. Okay, so here you can see that when degree is equal to 2, right? So when degree is equal to 2, you get W0 plus W1x, which is basically a line. It's same as the old linear regression. Okay. Now when degree is equal to 3, it becomes W0 plus W1x plus W2 x squared. Okay. So now you can see that you are already able to model a nonlinear function, just a linear model. Okay. So all I have done is added some nonlinearities to the input. Okay. So instead of just considering x, I'm considering x, x squared, x cubed, and so on. So in this case, it's degree of 4, and this is degree of 5. Okay. Now, degree 3 and 4 looks close to sign, right? However, when you look at degree 5, it's getting slightly deviated from the sign, right? Like so. Now the next, the interesting question here is like, what happens as I keep increasing the degree? Okay. Now here you can see more degrees. Like so, in this case, I have degree 6, 7, 8, and 9. Okay. Now, if you look at degree is equal to 9 solution, it exactly fits the data. So if you look at this function, you can see that it goes through every single point, right? So what would be the training error for degree is equal to 9 model? 0. Now, is this a good solution?
No.
No. Why?
Because of overfitting and the complex of the data and it's too exact.
Okay, so it's too exact, or in other words, it overfits to all the complex nature of the data, right? Like so, in some sense, this model is trying to fit every single point as possible, but it is doing it with the cost. The cost is you cannot generalize better, okay? Because for example, let's say I want to predict what would be the y for x is equal to 0.2. Now this model is going to have a very high value for that, right? Similarly, if I want to predict something like here, this model is again going to have a very high value, right? So it's going to have huge error for most of the cases that I want to generalize to, right? So in some sense, like the model is overfitting to the data. Okay, so we're going to call this phenomenon of fitting the data perfectly at the cost of generalization as overfitting. Okay, so when it is overfitting, then the generalization performance is going to be bad. Okay, now this is how we can define overfitting. Okay, so if a model is overfitting, okay, its generalization performance should be bad. Or in other words, the test error should be high. Okay, now I can actually try every degree of the polynomial, and instead of just looking at the training, like the function, I can look at what is the validation performance or what is the test performance. Okay, so here that is what we have done here. So if you remember, there is a train split and a test split, right? So I have considered different degrees of polynomial, and the blue line here is the training error. Okay, so this is a training error, and the red line here is the test error. Now you can see that as you increase the degree of the polynomial, in this case we had 10 data points, right? Which means if you have 10 parameters, which is what degree 9 is, then each parameter can kind of fit to to all these different like examples, and you have like 0 training error. Okay, so in this case you have 0 training error. However, it results in really high test error, right? So the first thing I want all of you to realize always is the goal in machine learning is not to get 0 training error. Okay. In fact, in most of the algorithms that we are going to see, we will never achieve 0 training error. So, like, it's okay if your training loss is not 0, but what is more important is your test performance goes to 0. Well, it's very hard to go to 0, but like go as low as possible, right? Like so this is a situation, okay, where overfitting is happening. Okay, this is a bad region to be in. So you don't want models in this region. However, if you look at this region, right, so where the validation, like the test error is also low and the training error is also low, right? Like so, now this is the good region. And you can see that in good region, the training error is not as good as the bad region, interestingly, right? So you still have some training error, but what is important is like your test error is at the minimum, so you should just pick the best. You should just pick the best degree, which helps with reducing the test error. Okay. However, I have a question for you. So now we all know that 3-degree polynomial is just a special case of 9-degree polynomial, right? Like you set remaining degrees to 0, you get a 3-degree polynomial. Then why is it our 9-degree polynomial not able to find the solution? Any answer? Yeah.
There are not enough data points.
There is not.
Data points, a 9-degree polynomial would be fine.
Okay, so there are not enough data points. Okay, that's a good answer. Any other answers? Yeah.
If the samples were exact, then we would have an exact answer. But,
no, that is not true. So I think, so even if instead of adding the noise, epsilon noise, even if it is exactly in the sine curve, you could still have problems.
I meant if it was polynomial. If the samples were from a polynomial.
Ah, okay, but we don't control that, right? Yeah, in the back.
Because we try to minimize training error, but we're not looking at all test error when we make the model.
Okay, so we are trying to minimize the training error, which is a problem, right? So this is something that we are going to talk in the next lecture about like empirical risk minimization, like where the idea is like we are only minimizing the training error while we should be minimizing the generalization error, right? Like, so, but the problem is we don't have access to generalization error. So training error is all we got. So how to do it carefully, that's what we're going to see today and in the rest of the course. Okay, all the answers were correct, okay? So now to understand this even further, let's actually look at the weights learned by all these polynomials, okay? So in this case, you see that when you have m is equal to 0, which means you just have the bias, this is the model. When m is equal to 1, you have the simple linear model, right? Like the line model, and these are the coefficients. This is a model with degree 3, this is a model with degree 6, and this is the model with degree 9. Okay, so now do you see what is happening? So can someone explain me now why degree 9 polynomial is a bad?
There's too much disparity between the weights of the biases?
Yes, well, it's not that. Okay, so it's not about the difference between weights and biases.
Like there's, like we go from 13 to 967 to 10,760.
Okay, yeah. Okay, so that is fine. Yeah, you have
I think there may be some errors when we do calculations numerically, because these constants have different orders of magnitude, and that might induce some error in the final answer we calculate.
Okay. Okay, but the question is more about like what can you infer from these weights, right? Like so what's your name? Shyam? Okay. So Shyam pointed out, like, so you see a lot of like high weights or large weights here, right? Like, so what is happening here is like you just had 10 data points. Okay. So in some sense, this model is giving very high weightage to these 10 data points, which is kind of represented in this very high coefficients that you're learning. So it like it's not fitting the data properly. Okay. However, in reality, like as he rightly pointed out, right? Like, so if you have more data points, then you cannot give this weightage, right? Like, for example, imagine instead of 10 data points, I had 100 data points or 1,000 data points. Okay, so then 10 parameters cannot do justice to all the 1,000 examples, right? So then they have to find the best possible solution, which is basically setting most of the things to 0, right? So, or in other words, this 9-degree polynomial, right? This model is expressive enough, okay, to model the sine function, okay? So it has all the expressive power to model the sine function, okay? However, but we are not able to learn that solution. Okay, so how do we learn that solution? So how can I use a 9-degree polynomial and get sine function out of it, right? Like, so, or in other words, like how to solve the problem of overfitting. Okay. Now, I think I get confused with this timing. So we started at 12:45, right? So I should not end now. Like I should end at 1:35. Okay. So somebody tell me. I thought it's a break time, but somebody tell me when it's a break. Okay. So how to solve this problem of overfitting? Yeah.
I just have a question. What if it was really a 9 polynomial curve? How can we know that the result that we have is
How can we have?
What if
Okay, that's a very good question. So the question is, how can we know that the true function is not 9-degree polynomial?
Yeah.
That is why I started with a synthetic example, because in this case we started with a sine function, right? Yeah. So in this case, okay, can someone tell me what is the degree of this? Yeah.
But if it was, the test data would be, error would be low.
Yes, yes, yes. So if it was actually a 9-degree polynomial, the error test error would have been low. So that is another way, like, to verify. In fact, that is how you are going to verify in real life data sets, like by just looking at the test error. That's a very good observation. But in this case, to make the discussion easy for us, I started with the sine function. So I know what is the degree. So can someone guess what is the degree of sine, this particular sine function? Oh, just for this curve. So I like not the entire sine function. So this is my data region. So I think this is a, well, like a rough rule of thumb is like see how many places it switches direction. In this case, it's 2. So roughly you can model this with a 3-degree polynomial. Well, okay. Now, okay, so how to solve this problem of overfitting? So I think you already have the first solution from, what's your name? Sorry? Louis Philippe. So we already have the first solution from Louis Philippe, which is just add more data points. Okay. So whenever you think your model is overfitting, if you can add more data points, then it grow the data. Whenever the data is beyond the capacity of your model, then it cannot overfit, right? So now here is the same sine example. Okay. So in the left side, you see the actual 10 data point data set. Okay. In the right side, I have 100 points sampled from the sine function. Okay. Now I'm using a 9-degree polynomial. Now 9-degree polynomial has 10 parameters, and these 10 parameters have to fit 100 examples. So now they cannot overfit because there are like way more examples than the parameters, right? Like so you can see that it fits very close to the sine function. It's not perfect, but it's much more better than the left side, right? Now, what if you cannot get more data? Like what if data is costly? Like whoever is giving you the data says no more than 10 data points. Like, so what would you do?
We
Raise first.
we can try to linearize data points which are very strange, like far from other data points.
Okay, so you made the transition easier. So that is what my second solution as well. Like, so just give me 1 second. So the second solution, as he suggests, is like you just penalize these weights if they grow too much. Okay, so you basically add a penalty term, okay, to the error function, okay, to discourage the coefficients from reaching larger values. Okay, so how do we do that? So we will see one example now, but we are going to see several examples in the future. So the example is a modified error function, okay, where the first term is exactly the same error function that we are used to, which is y hat of xn w minus y of n. Now, plus I'm going to add a new loss function, which is basically the L2 norm of my weight multiplied by lambda by w. Okay, now where this w square is the L2 norm, so it's w transpose w, or w0 square plus w1 square plus wm square. Okay, now we know that we are minimizing this loss function, right? Like, which means if I'm minimizing this loss function, I'm also minimizing w0 square, w1 square, which means I'm minimizing the weights as well. Okay, so I want a solution. I want a good solution for this linear regression problem. Okay, this regression problem, but with an extra constraint. The constraint is it also should have as low weight as small weight as possible. Okay, now how much important is this regularization, right? Like, so we're going to call this as regularization. Yeah, okay, so how much importance is this regularization term is given by lambda. Okay, so if you put very high lambda, it means you give like a lot of importance to regularization. If you put very low lambda, you're going to give less importance to this regularization. Okay, now we will see how this lambda works. Like, but before that, now this error function that you are seeing here, right, is still a quadratic error function. Is that right? It's quadratic with respect to w. We already know the first term is quadratic with respect to w. The second term is just w square, right? So the whole function is quadratic with respect to w, which means I can differentiate, set it to 0, and I have a closed form solution. Okay, we are not going to do that right now. So we will. The goal is to do that by end of the lecture. If we don't do it next week, but for now, let us just assume that somebody has done that for us. We are not even going to look at the solution. We are going to directly look at the visualizations. Okay. But just know that you can solve this. Okay, we are going to solve this soon. Now, let's say somebody gave a solver for this. Okay, now we can try different values of lambda and see how it affects the model, right? So in this case, you see that for there are two different values of lambdas that I'm using here. So one is, okay, so instead of directly changing lambda, I'm changing ln of lambda. Okay, it is just easier with ln of lambda. So the first value is, okay, when you have ln lambda is equal to minus infinity, it means lambda is equal to 0. Okay, so when you set lambda is equal to 0, you have only the first term, right? Let's go back. So here, if you set lambda is equal to 0, you have just least squares. So we already know that this is what the solution was, right? Now, I can have a reasonable range for lambda. In this case, it happens to be like minus 10 ln lambda, right? And you can see that the weights are already coming down, right? Now, if I put very high lambda, so you see that all the weights are going towards 0. Or in other words, you get almost a degree 0 polynomial, right? So now this means that when lambda is too small, okay, there is no regularization. when lambda is too high, then you have too much regularization, right? So it's actually very crucial to choose the right lambda, right? So how do we choose the right lambda, right? Like, so this lambda actually has a special name, okay? So we are going to call lambda as the hyperparameter of the model. Okay. Now, W is the parameter of the model, right? Like on the other hand, I'm going to call lambda as the hyperparameter of the model. So why? Because we will, if something is a parameter of the model, we will be learning it from the data. Okay. Now for hyperparameters, we would just randomly fix a value, like, or sometimes use a heuristic to fix a value. So you first fix the hyperparameter, let's say lambda is equal to 0.1. Then you start learning from data your parameters. Okay. Now, then the next question is, how do I choose this lambda? So how to find the right lambda? Any suggestions? Yep. Use the test set. So can we use the test set to find the lambda?
Like the validation, so like you have like 3 sets.
We haven't seen the 3 splits yet. Okay. That's the right answer, but that's what we are going to see next. So far, if you remember, we took the data and split it into train and test, right? Now we had only these 2 parts. So there are 2 questions to ask here before we think about a new split. So the first question is, can I use the test set to find the best lambda? Yeah?
Well, no, because it'll probably be overfitting.
Overfitting to the test set. Yeah, that's a good question. That's a good answer, but that's not all of it, right? So if you remember correctly, test set is meant to be a proxy for real life generalization, right? Like, so it is really this one last thing that you're evaluating before you deploy your system. So you should not see test set for any process in your pipeline. Okay, so if you use the test set to find the value of lambda, then the test error that you have is not representative of what you're going to see after deployment. Okay, so never touch the test set. Now the next question is, can I use a training set?
Yeah.
Okay.
You can reshuffle the data.
No. I'm not talking about, I'm talking about, can I directly use the training set to find the value of lambda? You?
No, because otherwise you'll be a normal parameter into hyperparameter lambda.
Sorry, can you please repeat?
If you train to find lambda, then it's not a hyperparameter, it's just a normal parameter of the model.
Okay, but is that the only problem? So there was another hand. Someone else raised hand. Like, is there any answer in the chat or yeah?
You try to set the value just by training on the traces and then testing on the traces to those bits.
Okay, so maybe I'll give you guys a little bit of hint. So now this is my equation, right? Now I'm going to find the best value of lambda by trying different lambda and computing the training error. Okay, even without running this experiment, you can predict what would be the value of lambda. Can someone tell me what would be the value of lambda if you choose based on training set? Sorry?
Like no regularization?
No regularization, 0, right? So if you're going to pick lambda based on training set, then the best possible lambda is just 0, right? So do you all agree? Like because if you set anything other than 0, then you are giving little bit more importance to this term than this term, right? On the other hand, we know that with the training set, to get 0 training error, you just need to focus on that. So in some sense, like, it's totally useless to do this with training set, because it's always going to say, no, don't regularize, because we started regularizing because we don't want to focus on the training set. Like, we wanted to focus on generalization error, right? Like, so we can also not use the training set. Okay. Now, how do we do this? Like, one simple solution, as somebody suggested, is instead of dividing your data into 2 parts, you can divide it into 3 parts. Sorry, I think I missed you from the beginning. Yes.
The another solution is to split the train data for some data for train and someone for valid data, which is for the validation of the.
Yeah, that is what I was going towards. So instead of having 2 parts, we are going to have 3 parts. Okay. So we're going to have train. We are going to have a new set called validation set and the test set. Okay. Now, this train data is what we are going to use for computing the parameters. Okay. We are going to use the validation set to fix the hyperparameter. Okay. Now, validation is a proxy to test set, while test set is the proxy to real life performance. Okay. Now, this makes the process cleaner because you don't see the test set at all. Okay. So the process is going to be something like this. Just give me 1 minute. So the process is going to be something like this. Okay. Now, for different values of lambda, okay, I'm going to train the model. Okay, and then I'm going to compute the performance in validation set. Okay, and then I'm going to pick the value of lambda that has best validation performance. Okay, and then I'm going to compute the test performance for the chosen lambda. Okay, now this process of choosing the best lambda, right? So this is also known as model selection. So different value of lambda gives you different models, and you're picking the best model by using the validation set. Okay, is this clear?
How do we select the size of the validation set?
Okay, so that's a very good practical question. So how do we split my data into train, valid, test, right? So now, if you are dealing with established data sets for a problem, then the data set actually comes with train, valid, and test. Okay, at least it will come with train and test. Okay, if they don't give you validation, like normal rule is you keep 80% for training and 20% for validation. However, if you have really huge data set, could even do 50-50. For example, if you have billions of data points, right? Like if you are in low data region, like you would try to do 80-20. Okay. So now, before we go for a break, I just wanted to show this. So here you can see that for different values of lambda, so what is the training error and the validation error? Okay. So now you can tell me approximately which is the best lambda value, right? Like so, like for example, this is an example of bad region, right? And this is also bad region. So probably this is the best possible value for lambda. This is the best possible lambda. So you're going to do this in your assignment as well, okay? So when you have a hyperparameter, you try different values and pick the best hyperparameter based on the validation set. Is that clear? Okay, so we will stop here and take a 10-minute break. So we're going to continue at 1:45.